All right, so exams on Monday, there'll be a review today with Raksha. So if you do want to attend that. And then the exam exam 4 is on Monday. And then next Friday is the final time period, so 8 to 10 a.m. So note the time difference. It will be in the Engman lab, so those are optional finals. So you can opt to take any of the exams that you've had throughout this semester. Whichever one is higher of the two between your original exam and the final portion that you take will be your grade that will be used. So you can opt to take that or not. You can just, if you are satisfied with what your grade is, then you can, that's weird. Then you can just, you don't have to come to even take the final.
Will the partial credit be put in before the day of the final, or will we?
So partial credit, I have to do manually, and so I will not have that in there. So one way to estimate what it will be is to look at your grade. If you've done a lot of extra credit, if you filled out the survey for sure, it will bump you up a half grade, and it could possibly bump you up a full grade. So if you've done both the course evaluation, anybody who didn't see that, please take that. It will bump you up a half grade. So if you're at 92.5 and you do the course eval, that will automatically bump you up to a 93. So that would be from an A- to an A. So it'll be that half grade bump with that. And then if you have a lot of extra credit, you'll get another half bump. So you can kind of get an estimate for about a full 1% in your grade based on what you've done for that extra credit.
So how are you going to know that we did the course evaluation? Should we email you? Or?
Yeah. So on there's a submission to just do a screenshot that I did the evaluation, and just the end, at the very end, it says you've completed the course evaluation. And so just upload that to verify that you did do the course evaluation. So a screenshot of that is all I need. Don't have to submit that would take away the anonymity of it. Yes.
Are there going to be first order equations on the
What do you mean by first order equations?
just like when we were doing the C, dV, dt, that kind of stuff?
So what you're going to see as far as for RC and RL, it will be what you've already seen as far as finding for VC or IL. And then it may ask you to use that information to then differentiate it. For example, possibly to be able to then find for dV or for voltage of capacitance, it might ask you to find the current through the capacitance instead, which would be I is equal to C dV dt. So you would have to differentiate it there. So you may see that. You won't have to solve the first order because we're just using the general form solution of it instead. Does that answer what your question is? Okay. All right, any other questions about what's on the exam or what will be on the exam? Or any questions about any of the material? Okay, so last time you guys just requested more examples, so we'll go through some more examples today. So these first few slides are, again, just more of the review, so we'll kind of go back up to them if needed. I had a request to, in one of my videos, I used this step-by-step procedure and showed that. So I've uploaded this to the handouts and lecture section. If you want to get it from there, there's a PDF of that. It's also now in these notes if you want these. These were created by Dr. Cotter, so I'd like to give him credit. He did a step-by-step procedure for these RCRL solutions. And then I also created a link on the handouts and lectures to his conceptual tools page. He has some other handouts like this and other information. If you like that style, you're welcome to go grab some of those and use whatever information off of those that you find useful. So he has some other procedural steps like these that I think he's done a good job with. All right, so that's kind of the summary of the step-by-step procedure from him. So we are going to go to this problem, which was 7.60. So we want to find V1 and V2 in polar form. So take a minute to try to solve this, to find this in polar form. Yeah, so this one with the current summation, which is a little bit
It'd just be like -4A something etc.
yeah, so if that was a voltage source, then it would be V1, you know, whichever direction was V1 minus V2 is
The
equal
kind
to
of
that.
yeah. Okay.
And then you would do a temporary current.
May or may not be good. I said,
is just like the number, so I just put that as well.
All right, so I feel that node voltage is probably going to be the best and easiest way to solve this. So so defining the current, so the current in this branch, V1 minus 0 over the summation of those, so 6 minus 4J. This branch would be V2 minus 0 over 6 plus or minus 4J again. And then this one I defined as the current going from left to right. It could be defined the other way. It's arbitrary. It goes from the plus side to the minus. So the plus side starts with V1, and then on the minus side is the V2 node. So V1 minus V2 over 12J. So defining those currents, I can then write the node voltage equation at V1. So 2 and 4 come in, and then going out is the V1 over 6 minus 4J, and then also V1 minus V2 over 12J. And then at node V2, I have minus 3J comes in, and then a V1 minus V2 over 12J comes in, and then 4 goes out, and V2 over 6 minus 4J goes out. Any questions about setting up these node voltage equations? Everybody's getting better with that one? Okay, yes?
The two going in, you're just summing them on the right side of V2.
V2.
It's the negative 3J and then, yeah.
So all of that is one node, so I have 1, 2, 3, 4 branches off that, so I need to account for all 4 branches. So that's one way to check is at a node, look at however many wires go out from it. And that's how many terms you need in there. And then I set what was going in equal to what's going out, but you could also say whatever's going in is negative, whatever's going out is positive, or swap that, whichever way you like to describe it.
So for your V1 minus V2 over 12J term,
Uh-huh.
do you have to keep that the same, or can you switch it to be V2 minus V1? What changes if you do that?
So if you switched it and actually defined it, whoops, going in this direction, you mean? This way?
Yeah, like for only one of the equations does.
So that purple one would be described by that one instead, V2 minus V1. And then in the V2 equation, I would have this go over basically to the other side. So it would be V2 minus V1. I don't know if that makes sense. So this would be over here. This would be V2 minus V1 over 12J.
Okay.
And then the one above, it would be the same thing. It would be on the other side with V2 minus V1 over 12J. So it would be over here, V2 minus V1 over 12J. Because it would be coming into.
So are you able to do like the red for the first equation and the purple for the second equation, or do you have to do them the same for it to work out?
I see. So You'll notice here that if I take that V1 minus V2 over 12J over to the other side, it's the same exact equation. So yes, you could do one for one and the other for the other. Okay, yes.
I guess I'm just confused why your negative 3j is positive in your equation.
What do you mean by positive?
Oh, I didn't see.
It's negative 3J. It's like, did I write that
I
wrong?
didn't see.
Okay. Other questions? So yes, it is still kept as negative 3J. All right, so then I used Wolfram Alpha. So I made sure, when I did type this in, I made sure that my equations matched up. You need to be very careful with parentheses if you're going to use any online calculator. Make sure those parentheses are correct to give you the right equation. So double check that it is matching with what you've written down. And then this gave it to me in rectangular form. So these were the answers in rectangular form. And then I converted that using the Wolfram Alpha app, or Wolfram Alpha website. It has that convert to polar. So I just plugged those two values in and was able to get that. So this is the answers for V1 and V2. Is that angle correct for V2? Okay. What quadrant is minus 162 in, or 116 in?
Is that how that 2 at the end? I can't see it. It looks like 1162.
116.2.
Okay.
0.2 degrees. Try to be more careful with my 116. So negative 116 degrees. Is that the correct quadrant? Yes, it is quadrant 3, correct. So, and that is where you expect it to be. A negative and negative would be quadrant 3. So this is quadrant 3. So Wolfram Alphas does it correctly. I think MATLAB doesn't do it correctly, so you have to check that one. Some of the other online tools may or may not do that correctly. So do make sure you're checking those quadrants and verifying. Photomath may not do it correctly, whoever wanted to use Photomath. Somebody may be in here or the other class, I can't remember. What quadrant is this one in? Correct. This would be quadrant 1. And it's also correct. All right, yes.
Can you show how you plug those into Wolfram Alpha to get the exponential form?
So on Wolfram Alpha, I just did convert rectangular to polar, and it pops up this conversion tool. And then I just put in that x coordinate and y coordinate. And then you can scroll down and it gives you the radius. So that radius is the magnitude. And then it gives you the angles and radians and degrees. It's a nice little handy tool. And I think it has a polar to rectangular too if you want. Let's see, polar to rectangular.
You don't include the I for the y coordinate.
Sorry, say that again.
You don't include the I when you put it in.
No, it just said the x and the y coordinate, meaning the x in the real axis and the y is your imaginary. So you do have to understand that to convert that. Okay, so it doesn't, Cartesian and polar coordinates. So it doesn't look like it does it backwards, but you can do rectangular to polar. Yeah, so Cartesian or rectangular to polar it will do.
Will it almost always, will Wolfram give you the final thing in rectangular for the most part? Will we like always have to convert to polar?
Typically it will, so it just depends on what you input. Sometimes it will be like, oh, there's another option and it will show you the polar underneath it. It just depends. Sometimes it does, sometimes it doesn't. I can't figure out when it does and when it doesn't. So just note that if it doesn't and you want it in polar, you need to convert it. All right, any other questions? Okay, so let's work on this one. So this one you're gonna do all of the steps. So you're gonna take it from the time domain into the phasor rectangular domain, solve for IL of t, or solve for IL in the phasor domain, and then convert it back into the time domain. So work on getting all those steps and solving this one. All right, I'll be back in a second. So just keep working on that.
Time domain to, phasor domain, time domain. That's like, is it equal to? Yeah. No. Cause like, so, cosine, I converted that to, cosine. Cause it just uses the
Okay, I like that.
Oh, yeah, so like, so that's where we got the 4 cosine, and then, you know, 4, like the amplitude e to j, like whatever. J. Yeah, cause it's, j times whatever that is called. Your phase shift, I think. So,
No, I'm talking about this, it's like a faucet.
You have to do every pathway there. Oh.
You don't need the resistance. You find the resistance across the
I don't know. We're just doing. No, I want the table. It's easy. It's just easy. I'm not speedrunning. No, this is our voltage. We're gonna put this that's it. No, we're gonna put VA.
Cause it's, JWL is the equipment for this. Oh, just straight JWL, so yeah, it's just. Those she gets.
Why didn't he put I? Is that a problem?
Yeah, but I think it would be better just if it's
Why is it not like it's so weird. You want who's right? Probably her.
Okay, so converting these to the phasor domain. So you take the sinusoid. Again, you need to make sure it's in cosine first. So this one's already in cosine. There's no phase change, so it's just 12e raised to the j 0 degrees. That becomes a 1. E to the 0 is 1. So that can just be written as 12. For the sine, you have to convert it into cosine first, which gives you that minus 90 degree shift. So then that one will be 4e to the minus j 90 degrees. Yes.
How did you get negative 50? I think it must be.
For 1 over, so this is 1 over j omega c. Omega is the 377. And then 20 over 377 times 10 to the minus 3. If you forget that milli, it won't be minus 50. So make sure you include those units. Is that what the error was? That's the most common thing I'll see is students forget to put in those units. So make sure it was milli. It's 10 to the minus 3. And then for the inductor is j omega L. And so omega again is 377 from the inputs, and then 10 over 377 for 10J. So you have this circuit. So this replaces with 12 for the voltage source, 4e to the minus j90 for the right side voltage source, 10J for the inductor, and minus 50J for the capacitor. So that is the phasor domain circuit. And then from there, I can do node voltage again. So I wrote the current in the left branch is Vx minus 12 over 20. The middle branch is just Vx over 10J. And the right side branch, Vx minus 4e to the minus j 90 degrees over the summation of those two. So 30 minus 50J or minus 50 plus 30J. Do a current summation for those three equals 0. And then I put it into Wolfram alpha. I double checked my numbers here, and the form here was exactly the same as my written one. Very easy to make that error when you're typing it in, so double check those always if you use Wolfram alpha or any other online calculator. It gave me the rectangular form, and then in this case, it gave me the option to change it to exponential, so there was that little box above, so I was able to just move it to exponential form there. Note though, when I change it, this is always going to be in radians, so I need to convert that into polar, or to degrees if I want it in degrees. So I can either use the tool online to convert it from this rectangular form into the polar, and then that gives me the option for degrees, or remember the conversion from radians to degrees is radians times 180 degrees over pi. Yes.
Is that the current ILT or the voltage? The V1?
So this is going to be your Vx. So my x was Vx. So from here, I know that IL is Vx over, what was it? Vx over 10J. So I can do this either, so this is 6.3 52.3677. E to the J 52.34 degrees. And 10J is J90. So I can just calculate this by hand if I want. It will be 6.3677 over 10. When you have angles like this, the exponential, you can take up the exponential and it's a subtraction on the top, so minus 90 degrees. Or I can use the calculator. So I can add in an extra, I'll just call it L, is X over do this one. What's wrong with this? Correct. So this is an example of forgetting to put the parentheses around, and you'll see it like that. The I will not be in the correct place. So you need to make sure that it's there, L over X over 10I.
For the exam, you're gonna want our Wolfram alpha calculations with the submission, right?
Yeah. Yep. So just like I copied them on here, just include them in your work. I'm just gonna skip to the exponential form of that. Actually, I'm not, because it doesn't give it in degrees. Going back. So 0.50411. So this gives the polar form of 0.6367 e to the minus 37j. Is that the correct angle? And that gives you that fourth quadrant, which is correct. So what will my IL of t be?
.6367 cosine 377 minus 37.
Correct. So the magnitude of 0.3663, dyslexic today, 6367 cosine 377t minus the 37 degrees. And this is in amps. Oops. So this would be my answer. All right, questions? Yes.
I was wondering, when you're finding, you did 10J to the 90 degrees, where did the 90 come from?
So converting this, I convert this easily in my mind of where is this vector. So if I was to draw this vector, it's just going to be right here, because the 90 degrees is going to just be right there. So it's a magnitude of 10 on that vector with an angle of 90, which you can rewrite as just 10J.
Well, why'd you do that in the first place, though?
So this is the example of, yep, so you can multiply and divide. It's usually easier. Why this? Well, that's bizarre. I don't know where that came from. Okay, sorry about that. So multiply and divide, you want polar form. Adding and subtracting, you're going to do rectangular form. when you have a division of exponents, it's just adding, so if you multiply and they add together, and if you divide, it's a subtraction. So that's the property of an E, of the E. Okay? Yes?
When you're saying to check the quadrant, what are you like comparing it to make sure it's in the right quadrant?
So this is quadrant 1, this is quadrant 2, 3, and 4. So I'm just thinking about like a vector that's minus 37 degrees is going to be here. And so I just want to go back to the rectangular form. And I see like, yes, it's a plus in the real and then a minus in the imaginary. So it would be there.
So you just want to make sure the conversion works.
Yep, just that the conversion is putting you in the right quadrant for your angle. That's what I'm checking. All right, any requests for additional types of problems? If you want me to have videos of those or just extra problems of any types? Okay. Okay. If any of you want to stay a moment longer, I can go through a quick example with these of doing something like that. And if you have to go, I understand. So.
At least for like the problems where it's like the DC current and it's you have the switch like t equals 0 minus whatever. And like real examples, you kind of put that switch in there.
Yeah.
So, really quick, a question on the, I think it's the first example we did. Your equation for V2, I'm just kind of confused how to value that for no. Here.
So this is going out. So there's my.
So plus 4a.
Oh, you did minus. So minus going out would be minus 4. Oh wait.
This is for
Sorry,
V1.
wrong one. Okay, yeah. So plus 4, and this would be a
V2 over 6 minus.
4d. Yep. And then this would be a minus, so it would become a plus.
Why is it a minus minus?
So minus because it's coming in, and then the value is a minus.
Oh, so plus, yeah.
So that becomes a plus, and then this one you defined as V2 minus V1
over J12.
Yeah, it's the same equation as I had.
Oh, okay.
Yeah,
It looks
it's just,
different.
yeah, just manipulated differently.
Quick question. When you went from the current is V1 over J, why did you put the 10EJ90 right there?
Because I want to, when I'm multiplying or dividing
Yeah.
by hand, I want to do it in polar form.
Okay.
So I do that because I know that when I multiply E components, they add together, and when I divide, the bottom one
so
subtracts
you just
off.
changed 10J into that because they're equal, and then just did it by hand?
Yeah, this was just to
Okay.
do it by hand.
Okay.
And it will end up with the same.
Okay, awesome.
Yep. Hi.
I have a question about just the node voltage. So in the example you had, all of the currents kind of like going into that node, so it's like plus is equal to 0.
Uh-huh.
Why wouldn't it have worked if I had, from the capacitance side, just from the right and left side, and then that was set equal to dx over 10j?
Wait, this one or was it this one?
Yeah, because I had it where it was this, so this plus this is equal to, and then this.
So you had V.
Yeah, so right here.
Okay, so you did minus V1 over 10J. Okay.
Yeah, would this have worked?
And then, yeah, so that would be, so the issue with this is that this was defined, and typically we can make it arbitrary, but in this case it was defined as going down. So you can find it this way, like yes, you could say going in is a minus V1 over 10J, and then here you had 12. Okay, so then it would be a plus V1 minus 12 over 20, okay, and then a plus V1 minus this over those.
It's because we're trying to find going out.
So you could define this either way. This one doesn't matter, but I don't know where these.
This
Oh, that's a
is
different
like for
equation.
finding I of L of T. 'Cause
Okay,
this
so
is
yeah,
this is
4
where
minus, okay, so V1 minus 4e to the minus
C1 is
90,
just
yeah, so, but this would be, okay, yeah, this would be 30 plus the C1 value. Yeah, so your equation's correct, you can solve it for V1, but then when you put it in to the IL equation,
this
it
is
has
just
to
gonna be
be,
10J. So
okay, so then it has to be a plus V1 over 10J,
a plus V1 over 10J.
Yeah.
Okay, all right.
and then that would be working.
Okay.
Okay,
you.
yeah. So for those that are staying for a minute, so if I wanted to find an example such as this where I found the IL and then I want to find the voltage, like the VL across the inductor, then I would use L DIL dt, and I would use this IL. So I go back to the inductor value is 10 over 377, and then I differentiate the IL. And I'm going to use Wolfram alpha to make sure my math is correct on that. So IL was 10 over 377, and then I just multiply it by, and you just type D of 0.6367 times cosine 377t minus 37 degrees, and then dt. And then that will give me so it gives it in sine, so you could write it in sine or you could convert it back into the cosine. So this ends up being 6.367, and then if I did convert it back to a cosine, it would be over 180 pi. Oh wait. It wrote that weird. It did write it weird. So you'd have to convert that back. Let's see, let me convert it. No, it won't let me convert it. So you would have to convert that back. Oh, there we go. Okay. It gave it to me in minus 377t. That's weird. I'm trying.
In order for that differentiation to work, does it have to be in sine or cosine form, or can it be like e to the negative whatever degrees?
Yeah, you can do whatever,
You can do it on
whatever form it is. It just takes the derivative of it. So this made it kind of weird, but this would be still the way you could do it, and just write it in the sine form. And this is also in radians, so you would need to convert that back into. So this would be radians. And then it's a minus weird number, but you could also use it to just graph it and find that value. So this is an example just to put that in there. All right, any questions from those that stayed? Okay. All right, have a great day.